Hi everyone, welcome back to another Planetarium live stream. My name is Jessica. I am the director of the Planetarium, and with me today are two of my students who work in the Planetarium. I'll let them introduce themselves, and we'll start with Eli since he's to my left.
Hi, I'm Eli. I'm a physics undergraduate student at UMD.
Hi, I'm Lindsay. I'm a physics graduate student at UMD.
So tonight we are going to be covering a super fun topic all about the many ways that we could be destroyed. I know it sounds like a total bummer, but there's some really cool stuff to talk about. So hopefully you end up overall enjoying it. Now throughout the show tonight, if you have any questions, leave them down in the comments and I will be checking through those and we will get to them when we see them. Or if we don't get to them right away, there will be time at the end of the show to cover any questions that we missed. So with that, I am going to turn it over to Lindsay, who's going to get us started tonight.
All right. So I get to tell you guys some of the fun, exciting, kind of more earthbound ways that the Earth could end, some internal things that could cause the Earth to end. And then Eli is going to talk about some kind of more of the more exotic things from space that could cause the Earth to end. So first, we are going to take a look at the likelihood of Earth being destroyed by an asteroid impact. So to kind of explain how we could possibly stop an asteroid impact, also kind of what kind of damage an asteroid could do if it did impact Earth, we are going to watch this video with none other than Bill Nye the Science Guy.
We've all witnessed the beauty of a shooting star, but what would happen if an asteroid was on a collision course for Earth? Could we detect it ahead of time? And more importantly, could we stop it?
I believe I have an answer. Now, you see, asteroid impacts are serious business. When I was in second grade, Miss McGonagall told us that the dinosaurs, the ancient dinosaurs, died out because they had small brains, maybe like my old boss. But even she knew that was kind of lame, that theory was nothing. It turns out, in my lifetime, people found this crater off Chicxulub, Mexico. This crater was so big. How big was it? It was so big that an asteroid hit the Earth, or impactors hit the Earth, threw so much stuff into the Earth's sky, it was bigger in diameter than the Earth itself. So the Earth was surrounded by red-hot rock for weeks at a time, cooked everything. And just the animals that lived in burrows and caves, our ancestors, led to us. So, serious business. You may recall, Valentine's Day 2013, Chelyabinsk, Russia. Airburst. See, if you're an asteroid and you're going 10 kilometers a second, 20 kilometers a second, and you hit the Earth's atmosphere is like concrete. It can't get out of the way. So the asteroid just explodes, an airburst. So these asteroids are serious. Most of them are very small. If you're under 10 meters in diameter, you hit the Earth's atmosphere, you burn up. Big blue streak, blue green streak, white streak, and then humans make wishes upon you. I don't know how efficacious those wishes are, but people do that. All right, so if the asteroid starts to get bigger, starts to get into the 25 meters, into 45 meters in diameter, then you get Meteor Crater, Arizona. Wham, huge thing. That would be like a city killer or a county killer. And then when they get to be 100 meters, 140 meters, now you're into a country killer. And then you get bigger than that, it's a continent killer. Much bigger than that, and you're taking out whole races of ancient species. So, what if we found an asteroid that was headed our way? How would we find it? How would we find an asteroid headed our way? That's a good question. Well, you can use telescopes. Skilled people can point the cameras at the sky and look for fast-moving objects that are crossing the Earth's orbit. But we're missing perhaps 100,000 of these things, of these county killers, city killers, country killers. So what we want to do is build a spacecraft called the Sentinel. And as we say, it's like looking for a charcoal briquette in the dark. These things are hard to find. They're tiny compared to the vastness of space. But infrared light, heat, bounces off of them. So what you'll do, you're a satellite, you're a surveying spacecraft, you'll get your back to the sun and look out from about the orbit of Venus and try to find all these asteroids. And then you find one, what do? Do you run in circles screaming? Ah! No. We've got to deflect it. Just a little, just a tiny amount. Asteroid might be going 10 kilometers a second. We want to change its speed about 2 millimeters a second. So 10 kilometers, that's 10 times 1,000 meters. That's 10,000 meters. A millimeter, that's 1,000th of a meter. So that you take the 1 over the 1,000th, it's 1,000 times 10,000, that's 10 million. You want to change its speed at 10 millionth of its total. That's not very much. But if you're an asteroid that comes in at 10,000 tons, 100,000 tons, it does take quite a bit of force to change it a 10 millionth of its speed. Okay, how do we do that? Well, the easiest way is to get a rocket, just a big rocket. Just go out there and just smack into it. Except it's in outer space, so it just goes like that. Okay, and that would change its speed a little. Now notice, everybody, what if it's not just a rock? What if it's a pile of rocks just loosely held together by primordial gravity? And so if you hit them, they'll just spread out and you'll have a shower of rocks. That would be bad. So how about this? We'll get a big spacecraft that's massive spacecraft, and we'll go out there and just get near the asteroid. Just get near it. And then the mutual gravity of you, the asteroid, and me, the spacecraft, will tug the asteroid speed just a little bit, just a tiny bit, or maybe get on the other side and tug this. That might work, but here's the problem. You need a huge amount of fuel for days and weeks and months and years. And what if it stops working? You can't go out there and fix it. Okay, how about this? The laser beams, a swarm of sunlight-powered lasers that are zapping the surface of the asteroid for days and weeks and months and years. Zap, 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 zap. So some asteroid, some rock is vaporizing, and the ejecta, the stuff ejected, has momentum, just like rocket fuel, just like standing on a skateboard and playing catch with a bowling ball, the way you do. And so it would then cause the asteroid to change its speed. And so you send a swarm of these laser spacecraft so that if one of them stops working, you can use the other one. Or you can have them come in from all different angles. And what if the asteroids are regularly shaped like this? You could beam it when the thing is smooth, and then when there's a pit or an inefficient place to be beaming, you turn off. You wait for the asteroid to turn. Then you turn it back. See, everybody, just because it's unlikely doesn't mean it's not a big deal. You know, if it only happens once every few thousand years, well, if it happens on my watch, it would, as the kids say, suck. Okay, so we don't want that to happen. We want to avoid that. Asteroids are serious business, but they're exciting. Except we're in space, so it's just. Got a burning question? Well, be sure to subscribe to ASAP Science. Follow us.
All right. So as Bill said, there have been a lot of different asteroid impacts on the Earth. A couple that we can still see kind of the effect of when we look at the surface of the Earth. One of them is the Sudbury Impact crater. So we can kind of see this like oval shaped disturbance kind of in the surface of the Earth. And this particular impact crater is actually up in Canada. The meteor that made this crater crashed into the Earth about 1.8 billion years ago, and it crashed through the rock that was, of course, there at the time. And the rock that was there at the time was called the Canadian Shield. And if you didn't know this, fun fact, Canadian Shield, only a few hours from us here in Duluth, has some of the oldest rock on the surface of the Earth that we've been able to find. So this meteor crashed through Canadian Shield rock that was about 2 to 2.5 billion years old, and left this 200-kilometer across impact crater. But when it did crash into the Canadian Shield, it actually tossed up a bunch of what's called ejecta, or material, and we actually can find evidence of this Sudbury impact in the stuff that it went up into the atmosphere, sent up into the atmosphere in northern Minnesota. So all the way down in Minnesota, we can see evidence of this Sudbury impact. This is called the Redefort impact. And you can see kind of the ring right here. This is actually a double ring one. So we have an inside ring and then the outside ring. So this meteor that created this crater, so this is in South Africa. This crashed into the surface about 2 billion years ago. And it is thought to be one of the largest asteroids that has ever hit the Earth. And putting it up with the Sudbury Basin and then the Chicxulub crater, which I'll get to next. At first, it was thought that maybe this was a crater from a volcano, but after looking at more information about the rocks that were in the area, it was found that it was in fact from a meteor. So of course, probably the most famous impact is the Chicxulub impact, which of course caused the extinction of the dinosaurs. So this is where it is. Because it's kind of, at the bottom of the ocean now and stuff, we can't see the rings of this particular impact like we could with like this one, the Redefort impact. But we still know it's there because we look at the rocks underneath the surface, the ocean's surface, and we can see evidence of a meteor striking there. We see rocks that are not typical to Earth, and so they must have come from somewhere else. This impact created so much debris up into the atmosphere that almost entirely around the entire world, when you look back in the geologic record of the rocks, you see this like dark layer of kind of ash and silt left over from this meteor impact. So again, the ash from this and the debris from this impact ended up in the atmosphere and kind of spread throughout the Earth. Definitely caused some cooling and things like that to happen. And because those clouds that were up in, or the debris up in the atmosphere was kind of blocking out sun's light, that's partly, along with a few other things that happened because of the debris in the atmosphere, that blocking of the sun's light kind of made a lot of the living creatures at the time die. So there is a scale that scientists have made about the different kind of hazards of different asteroids that could potentially reach the Earth and crash into the surface. So of course, 0 is no hazard at all. Normal is around a 1, so there's a pass near Earth that's predicted, but probably no level of danger necessarily more than any other asteroid that's passing by the Earth. So we have then levels 2 through 4, meriting attention by astronomers, so getting a little worse there. And then threatening levels 5, 6, and 7, and then certain collisions 8, 9, and 10. So this is before the meteor actually strikes the surface and kind of predicting how much or how certain the collision is and kind of how much destruction that it might create. We do not have hardly any asteroids that we know of right now that are even on the Torino scale. Most of the ones that we know of are rated at 0. There is only one, that's rated at a level 1, but that is not slated to kind of come near us until 2069. Before that, we will have a couple of other close calls, but you need to really make sure you're looking at the units and the way that like the distances are being measured. So like if we look at this meteor called Apophis, if there are any Stargate fans, that's what it was named after, one of the gods in the Stargate TV series. So it is going to be at its closest approach to Earth in 2029. It was discovered back in 2004. And at the time when it was first discovered, it was thought that it was going to be one of the most dangerous asteroids for the Earth. But since then, we've kind of calculated the orbit better, and it's now also a 0 on that Torino scale. It's going to pass by at about 0.1, the distance between the Earth and the Moon. So that's what LD means. LD means lunar distance. So 0.1 of the lunar distance, which is still 38,000 kilometers. So a lot of people like to look at this like 0.1 of the lunar distance and think that that's going to be really close to the Earth, but the lunar distance is very, very big, very long, lots of thousands of kilometers. And so even though it's going to be 0.1 times the lunar distance, it's still going to be 38,000 kilometers from here. So, whoops, sorry. The kind of next ones that we have to worry about, 2028, 2001 WN5, that's going to be even further though at 0.65. And then in 2032, we have this 2008 DB at 0.32 lunar distances. And then in 2034, we'll have 2014 HB 177, and that'll be at 0.23 lunar distances. So the important thing to remember though is these are the asteroids that we know about so far. If you come down and look at some of the asteroids that we had kind of come through our atmosphere and impact this year in 2020, the date of closest approach and the date they were discovered is the same. So a lot of asteroids are just too tiny and difficult to find like super or way ahead of time so we can prepare for them, unfortunately. But you can also see that these two asteroids that came at closest approach this year came a lot closer to the Earth than any of these other asteroids are going to come in the coming years. And so these ones in 2020 didn't end up impacting the surface. And so maybe these won't have to worry about these either. All right, so next, super volcanoes. This is a map of all of the different super volcanoes that we think exist around the Earth. One of the biggest ones is over here in kind of Indonesia, and then the Yellowstone caldera in the United States. So Toba, so each of these circles kind of shows you the amount of magma that erupted from different volcanoes. So if you remember the Mount St. Helens eruption, well, not all of us were alive, but you may have seen videos of the Mount St. Helens eruption in 1980. Or Mount Pinatubo in 1991, they're all the way down here. And so all of these Yellowstone caldera eruptions, Yellowstone Mesa Falls, Yellowstone Lava Creek, Yellowstone Huckleberry Ridge, all of those magma amounts are much, much bigger than any volcanoes we have seen, in recent times. Toba, this super volcano, is the one that is in kind of Southeast Asia. And then the Long Valley caldera is one that is in California, actually. But we're going to take a closer look at the Yellowstone caldera because that's the one that most people are most worried about. We have all of this magma underneath the surface of the Earth right now that is causing geysers and hot springs. And we are currently kind of monitoring the area for earthquakes to see if there might be an increase in earthquakes. That might mean that this caldera is more likely to erupt soon. It doesn't look like that's likely, though, that the Yellowstone caldera is going to erupt anytime soon. When it does, though, it will be very, very bad if you are living in the Yellowstone area. You will die. Probably most things are going to die. So these different colors kind of show the different amounts of ash that are going to kind of go up into the atmosphere. And you can see that the ash from the Yellowstone volcano is going to cover the entire United States. So you will not be safe, completely safe from it anywhere in the United States, unfortunately. But again, not very likely. All right, so another thing that people like to talk about is the magnetic field reversals. And so this is going to kind of tell you what is going on in the center.
The difference between imagining the future and being the future is what you do to get there.
Sorry, I don't know why it's making me show the ad.
Only you can make you better. We can go hundreds of thousands of miles into space, but when it comes to inside the Earth, we have barely scratched the surface. Hey diggers, what's shaking? This is D News and I'm Trace. If you look down right now, you probably see the floor. But under that floor is dirt, and way under that is bedrock, and under that, hypothesis and theory. Seriously, we have gone to the moon, but the deepest we have ever been on our own planet is 2.4 miles into the crust at the Tautona mine in South Africa. What's down there? How does it affect us? New research has some insight. Scientists throughout history have mapped the inside of our planet by measuring the movement of seismic waves generated by earthquakes. Like sound waves, these are reflected and refracted, and they change speed as they pass through rocks of different densities and flows. Geologists believe as the primordial Earth cooled, heavy elements sank to the middle and lighter elements floated to the top. The result was a multi-layer planet. The crust is the top 25-ish miles, then a 1,800-mile thick inner and outer mantle made of highly pressurized superheated rock, which flows really slowly like asphalt on a hot day. Under that is an inner and outer core made of heavy metals. This is where we think our magnetic field comes from. The outer core is a hot liquid iron alloy, and the inner core is probably solid nickel and iron. Thanks to some new computer models from the University of Leeds and the Swiss Federal Institute of Technology, we've modeled the inside of the planet 100 times more accurately than ever before. The new model has revealed the moon-sized inner core is super rotating in an easterly direction, and the outer core is flowing much slower in a westerly direction. This opposing rotation is like a generator that we think creates the magnetic field of our planet called the geomagnetic dynamo. Doomsday predictors complain about this field switching or disappearing altogether, but science has shown the magnetic field has already done that. Back in 1692, Edmund Halley, like the comet, showed that the Earth's magnetic field has a westward drift. And by looking at 30,000-year-old lava flows, geologists can tell it's also drifted eastward at times. That's not really what these doomsdayers mean, though. They mean a pole swap. North becomes south, south becomes north. OMG! This has happened too. 780,000 years ago, during the Stone Age, the magnetic North Pole was actually on the bottom of the planet. Science! Now, with the help of these computer models plus centuries of seismic tests in geology, we know more about how the core of our planet works and also the magnetic field. The swapping isn't going to do anything too crazy. A switch of east-west drift ain't a big deal. We have to adjust for that anyway because the magnetic North Pole isn't perfectly aligned with the North Pole. It's drifting westward 1 compass degree about every 5 years or so. But a switch of the north-south field would take between 1,000 and 10,000 years and would definitely affect humans. During that time, compasses wouldn't work, and scientists think our weakened magnetosphere wouldn't block cosmic particles as easily. This would cause more intense and frequent aurora, cool, but maybe other problems like ozone holes and maybe increased cancer rates. No one's exactly sure. So what do you think of this? Are you worried? Spill the beans, and thanks for sticking around with D News today.
So he talked about in that video evidence of the magnetic field reversing, and that this is what we see at the bottom of the ocean. So in the middle of the ocean, there are these mid-ocean ridges, and they kind of have two plates on either side of the mid-ocean ridge that are flowing apart from each other. And as they flow apart from each other, magma comes up and fills in that ridge. So when the magma comes up and fills in this ridge and solidifies, it actually records the direction of the magnetic field. And so during this gray time, the magnetic field is like it is now. And then during this time where we have this white area, that would mean that the magnetic field was reversed, and then it would come back to how it is now. So we definitely have evidence that this has happened before. Again, the outer core is kind of liquid iron, and it's convecting and moving around, and that's helping to create the Earth's magnetic field, but we're not exactly sure how stable this kind of movement of the outer core is, and so it could be that that movement is not very stable, and that could be the cause of the magnetic field rotating sometimes. We're not 100% sure about that though. So during a reversal, again, we're not entirely sure what's going to happen. We don't have a ton of really great records because we only have reliable kind of magnetic field records for the past tens of thousands of years, as long as the ocean crust has been created. So we have, of course, now we have the field oriented so that we have the north and the south. But during those reversals, I mean, it could be all sorts of crazy. And we're not really sure how long a reversal is going to take. It could take, like you said, anywhere from like a year to 1,000 years. The magnetic field could possibly become weakened during this reversal. But again, we're just not 100% sure what is going to happen. But probably for the most part, it's not going to weaken so much that we have to worry about kind of mass extinctions happening. There is no evidence between magnetic pole reversal happening and also mass extinctions happening. They don't happen at the same time. But there could be a huge problem if a solar flare, super solar flare, happens to happen during a reversal and there's a weakened magnetic field. And that is what Eli is going to talk about.
Yeah, so just give me a moment. I got to get my presentation window up. Okay, cool. Can someone tell me if it looks all right once I share it? Does that look good?
Yep, you're good.
Okay, cool. So yeah, the magnetic field also acts as a shield for us from material that the sun throws out into space in events called coronal mass ejections, which are related to solar flares. And so one possible scenario of a doomsday on Earth from space comes from a irregularly powerful solar flare. So a solar flare at just basically is when the sun's magnetic field reorganizes itself. So when a lot of electrically charged stuff, atoms, things like that, are moving throughout the sun, they create these random magnetic fields all over the place. And sometimes they get kind of like twisted up in one another, and then you could say the field lines like snap and then reconnect to the sun. And when that snap happens, it throws a bunch of stuff into space, like charged particles. And that's what a coronal mass ejection is. And so sometimes when things are aimed perfectly, those particles will come towards Earth. And usually we can sleep easy at night knowing that those particles are kind of helpless against the Earth's magnetic field. What actually tends to happen is these charged particles interact with our magnetic field, and then they're kind of corralled to the poles. And then once they get to the poles, they've lost energy. They're not like really, really dangerous particles anymore. But they will smack our atmosphere, and it makes the atmosphere glow. And that's what we see as the northern and southern lights. So usually we like those because, you know, you're checking your northern lights radars to see when you should go to Hawks Ridge and try to find them. But it is possible that a really, really powerful solar flare could kind of overwhelm our magnetic field and our natural defense system. And you don't have to be worried that that the solar flare would send stuff that would like fry Earth or, you know, blow something up or anything. It's not, that's not the worry. The worry is that once these charged particles get down to the Earth's surface, they would kind of take our infrastructure to its knees pretty quickly. Because these charged particles would cause huge like current surges in our electrical systems, and they destroy these transformers which supply power to huge areas, and we would be without power. And that doesn't sound so bad at first, but you're looking at GPS, you're looking at like control systems for satellites, stuff like that. You're looking at hospital equipment, so like hospitals wouldn't really be able to function anymore, and it could turn into a problem pretty quickly. And this actually has happened before. I don't know the exact year. It was the mid 1900s, 1940s, I think, somewhere around there. A coronal mass ejection was particularly powerful, and it shut off the power for 6 million people in the Canadian province of Quebec. So this has happened before. It's never happened on a doomsday scale, and it would maybe be hard. I mean, I know we have ways to fix power supplies quickly and things like that, but it is a possibility. And should we be done there? Because I think we're at time.
I think it's okay. Go ahead and do the rest of yours.
So the next scenario that I wanted to talk about that I was pretty excited to look into is what if just like a surprise black hole snuck up on us and was right next to Earth? And in looking at this, I found kind of two different interesting scenarios. So we don't know, and we don't think. I shouldn't say we don't think, but we have no reason to believe that there are, you know, like really small black holes that, you know, we don't see, or they come in and out of existence randomly. We don't think that's how it works. But let's just say, for the sake of fun, or maybe not fun, that one like the size of a nickel appears right next to you. So do not be fooled by its size. This is still absolutely devastating thing. And if it appeared right next to you, the first thing that would happen is you would be spaghettified and torn to shreds almost immediately. And then what would happen is, since it would be like an orbit between the black hole and the Earth, but the center of mass would be so close to the black hole that the Earth would just kind of be spinning around the black hole. But in order for that to happen, the black hole would actually start eating through the Earth. And then I thought this was really interesting, but once the black hole got through there and the Earth was moving around orbiting it, the black hole would just kind of carve out the Earth from the center, and we would just have like a hollow Earth. So I thought that was interesting. Now, if we say that we have like a stellar mass black hole that appeared right next to the Earth, just like an average stellar mass black hole, be about half the size of the moon, but it would pull us with the force of over 300 suns. So really, really quickly, we would move towards the black hole until Earth as a whole was kind of torn apart and the chunks of it spaghettified, and then the same thing would happen. It would get eaten by the black hole. So don't really have a good outcome in either of those scenarios. But like I said, we don't really think that happens. So not too much cause for concern there. This is another animation of black hole right there. It's these kind of mirror what we saw in Interstellar, which I think is really cool. I really like this GIF. So my last one that I researched was also fun, and it was gamma ray burst, which I'm going to call GRB from now on to reduce lengthiness. So GRB is a really, really powerful expulsion of light and material from highly energetic events, such as something called a hypernova, which is the collapse of a really, really big star into a black hole, and it happens really fast. And upon that collapse, an accretion disk, so all the stuff that was around and maybe some excess stuff from the star starts orbiting the black hole that appears really quickly. And it orbits it in this ring. And that ring would have a bunch of charged particles in it. And those particles would create these fields that would throw stuff off of the poles of the black hole. So you'd have like the two beams, like you can see in this photo. There's that beam coming off of one of the poles. That's what would happen. And the stuff that comes off is moving extremely fast. So these jets also release a lot of gamma rays, which are really energetic and would be really bad if they hit Earth in a really, really concentrated amount. So this is an image of a GRB detected in a galaxy way, way far away. And you can just barely see it if you look at the frame labeled July 3rd, 2013, and then compare it to the June 13th frame right above it. In the July 3rd one, you see this bright blue pixel there that you actually don't see up in the June 13th frame. And that is a gamma ray burst. So like all the others, this one was intensely powerful, but it had little to no effect on the Earth because we are so far away. And all of the gamma ray bursts that we've seen have been from really far away. So right now we have no cause for concern from any of those. But again, for the sake of fun, if we were to say that one happened in the Milky Way and it was aimed at the Earth, which would also be probably unlikely, it would all but obliterate Earth's ozone layer, which would allow really, really devastating amounts of ultraviolet radiation to reach the surface. And those are really, really harmful. They cause cancer, and they would really hurt like wildlife and ecosystems. So we'd see kind of like a collapse of how things work down here. But as well as that, they would, I thought this was really interesting, they would create what's called photochemical smog. So as they hit the atmosphere, chemical reactions that would happen in the atmosphere would make molecules and compounds that don't let light through very easy. So we would kind of be covered in like a layer of like shades. So we wouldn't get much light on the surface. So not unlike what the dinosaurs experienced after the, I'm probably going to pronounce it wrong, Chicxulub, is that right?
Chicxulub.
Chicxulub, okay, after the Chicxulub impact, they would kind of go into what they call a cosmic winter, which would also make photosynthesis really difficult, and then animals could eat the plants, and it would kind of be a redo of what happened back then. So not exactly the violent and spectacular ending that you kind of picture when you think of a beam coming at Earth, but it would be an end nonetheless. And that is all I have. So I'm going to stop sharing my screen.
Awesome. So just want to kind of reiterate that all of these scenarios are very, very, very unlikely. So it's hopefully nothing that's going to keep you up at night or give you nightmares. But it is just some kind of interesting ways that, we might be in trouble in the future if this very unlikely thing were to happen. But thank you so much, Eli and Lindsay. That was awesome. I'm not seeing any questions. If you do have any, now is a great time to leave them down in the comments for us. And I will tell you a little bit about what's coming up over the next week. So Saturday is August 1st, which I still can't believe. And so we will be doing our monthly What's Up Tonight and tell you what you can find in the August night sky. And then next week, on Wednesday, I am now forgetting what we're doing. Wednesday, we're doing constellations, right? Constellation story time with our new sky for August. And then on Saturday, we are doing a new show called Learning from Light, because as astronomers, that's pretty much all we have to work with. And there's actually a lot that we can find out just by looking at light. And so we're going to take you through that. All right, well, I'm not seeing any comments come in, so we will wrap it up. Thank you, everyone, so much for joining us tonight. If you would like to see any streams you may have missed in the past, you can find them on our YouTube channel or in the video section of our Facebook page. So we hope you have a wonderful evening, and we will see you again next time. Bye, everyone.